Okay, so let's go ahead and see how much one stage of gas diffusion will affect our relative abundance for uranium. Now we're using natural uranium, so it'll be 0.711% by weight, and it's going to have an atom fraction of 0.00720. So first off, let's calculate the relative abundance. So for that, I need to know, well, how much do I have of the lighter versus how much do I have of the bigger? And so we're assuming that U-238 is, whatever is left after we subtract out the U-235, which would give me a relative abundance at the beginning of 0.00725. So there are very, very few U-235 atoms compared to U-238. As a note, there's also another isotope, which is pretty rare, which is U-234. But it's so rare that we're just going to ignore it, and it won't really change our numbers much to do that. So we can do that without too much of an error. Now, we have a relative abundance, but how much does it change after one stage? Well, let's calculate the separation factor. And at first, we're going to assume that it's perfect. So simply the mass of the heavier one over the mass of the lighter, all under square root. So U-238 versus 235, this isn't too bad, but this isn't U-238 and U-235 by itself. This is uranium hexafluoride. So hexa, that's 6, fluoride, atomic mass of 19. So that's where that 6 times 19 comes from. So I get there is in an ideal situation, one stage would have a separation factor of 1.0043. Now this isn't realistic because we're going to lose, it's not going to be perfectly efficient each time. So we're going to use 1.003 to be more realistic and go with what you would actually have seen in a gaseous diffusion separator. Now, having done that, we can figure out what our relative abundance will be after one stage. So it's just simply my initial relative abundance times my separation factor, which comes out to be 0.00727. So it changed by just a little tiny bit. It's not all that much. So how many stages would it take to get up to 90% U-235? Because, that little stage was really, really small, and that's not very helpful to see how much one stage does. I want to know how many stages I need to get to, some really weapons grade, I guess, U-235. As note, you do not use this heavily enriched uranium in a reactor. That's way too much. Okay, so what we'll do is we'll start off by making a general equation here. So if after one stage, R prime is equal to my separation factor times my initial relative abundance, well, then I can say, okay, well, that's just multiplying by alpha each time. So I could say then that my, product at the end is equal to alpha, my separation factor, times the number, raised to the power of the number of stages, multiplied by my initial, or my feed, relative abundance. Now, I want to solve for the stages, so I'm going to take the natural log of both sides. And when I do that, I get an equation like this. This will bring the s down from being an exponent. So I have the log of my ratio, of my abundance ratios, goodness, over the log of my separation factor. So this is looking pretty good here so far. But I do need to figure out what my relative abundance would be when I have that perfectly 90% enriched uranium. This is not a crazy one to do. It's simply saying that now I have 90% U-235. That goes on the top just like last time. And what's left, well, 1 minus 0.9. So only 0.1% of that, or 0.1 or 10% is U-238 at the end, which gives me a relative abundance of 9 at the end versus the beginning. So with that, I can just plug everything in. What I find out is it would take me 2,400 stages roughly to get there. That is a lot of stages, okay? And while I could possibly try to feed this back into a single system after running it through one time, it's not, it would just take forever for that to be the case. So what you're doing is you're having a bunch of different gaseous diffusion stages, one after the other, that you're constantly having this flow through. And in doing that, you can produce quite a bit per day, but it still takes a lot of energy to do so. Now, this is a relatively inefficient process. And also, you have so many components with all of these chambers and all of the membranes and all of the pumps that are getting you up to the right pressures the entire time, that it made this really economically unviable. So we shut all of these down in the past few decades. And we moved on to something that works better. What is that? Well, you'll find out next time. So I'll see you all in a bit. Bye-bye.